Hi, I'm Parker Harstead, and I'll be doing problem 8.7 in the book. So first off, we're given two tables here of 3 different cables of different types of polymers. You can pause to read these as you need. But the gist is that we have 2 blocks. Let's call it block A and block B. Let's make B a little bigger. And we'll have 3 cables in series here, in parallel here of different sizes. So let's make this one a little droopy. And this one's even longer. Label this 1, 2, and 3. And what we're tasked with finding is the force required to separate blocks A and B to 5 feet, making this length equal to 5 feet, when we cut cable 3. Okay? So the solution to this problem starts with equation 8.23 in your book, which is right here, where we have sigma is equal to RTN times alpha minus 1 over alpha squared, where sigma is the tensile stress, and R is the ideal gas constant, T is the temperature, and N is the number of moles per volume. Now, in the same page of the book, we know that sigma is equal to the force times the cross-sectional area when we're talking about tensile stresses, and that alpha, a couple of pages earlier, is equal to the stretched length over the unstretched length. So using those equations, we can set up a series of equations to solve for effectively this RTN here, where we know that sigma equals RTN times alpha minus 1 over alpha squared. And since we have 3 of these different cables, then we'll have a sigma 1, a sigma 2, a sigma 3, etc., right? So if we want to find the total force, Ft, of the system, it's equal to the force of cable 1 plus the force of cable 2 plus the force of cable 3. And we know that these forces are sigma times the cross-sectional area of each component. So what that looks like is effectively Ft equals sigma 1, or RTN times alpha minus 1 over alpha squared of each component. But now that, times the cross-sectional area of the component. But we know that this gas constant is constant, will be under a constant temperature, and since we have no change in moles per volume of any of the cables, we can actually jumble these together into an arbitrary constant. We'll just call this constant E. And since we can jumble these constants together, we can then have the sum of all forces is equal to E1 times alpha for cable 1 minus 1 over alpha for cable 1 squared times the cross-sectional area of cable 1 plus E2 times alpha for cable 2 minus 1 over alpha for cable 2 squared times cross-sectional area of 2 plus E3. You get the idea. oh, this is a 3. Times cross-sectional area of 3. Okay? So we have this set of equations here, and we'll look back into the table that we're given, and we see that we have a distance between all these cables. We have cable 1 is 2 feet, cable 2 is 2.5 feet, cable 3 is 3 feet, and I want to bring some light to a couple of different things. We have a few different units here. We have centimeters and feet, and then we have force in newtons. So we'll want to make sure that our units are all similar, of course. So we're going to want to convert these centimeters into meters by just multiplying by 100, 0.0025, 0.005, 0.0035. Okay? And you can do that on your paper. And then looking at this table right here, we see that at a distance of 2 feet, we have 0 newtons, which effectively means that there's 0 stretch across any of these cables right now. So then, seeing that at 2.35 feet, we have 100 newtons, and since we go back to looking at these, you can see that these are longer, obviously, than 2.35 feet, which means that 100% of the force is going to be enacted on cable 1 in this instance. This lets us in on something really good that we can help start to solve this big equation. And that is F of t, when equal to 100 newtons, is equal to E1 times alpha 1 minus 1 over alpha 1 squared times the cross-sectional area of 1, because these both go to 0. Okay? And knowing that, we have alpha 1 in this instance is equal to the stretched length over the unstretched length. So 2.35 feet over 2.00 feet, which is equal to something in my notes which I didn't write down. So anyway, in any case, we know that this alpha is equal to 2.35 feet over 2.00, and since it's feet over feet, it becomes unitless. So knowing that, we don't actually have to worry about our units in feet. What we do have to worry about is these centimeter units, because that will not become unitless. That's during our cross-sectional area calculations. So we'll do this alpha, and then for cross-sectional area, it's just equal to pi r squared. And r is, what is r? 0.0025 meters squared times pi. And now, so we know A sub u, we know alpha, and we know our force. So all we have to do is solve for E1, which comes out to, since we know it's an arbitrary constant, it might be a pretty big number. It's 4.7438 times 10 to the 6. Okay, so we have one of our unknowns, right? And so, using this table, we can see that we have all of the information to solve for all alphas in every case, and all of the information to solve for every cross-sectional area of every cable. So, using that, we know at any point the force, we know our E1, we know our alphas, we know all of the cross-sectional areas, and the only two that we're missing are E2 and E3. So we can set up a series of equations pretty easily. And that comes out of the next two distance and forces. So we can set up a series of equations using our known force of 485 and our known force of 625. And it shows like this. 485 newtons is equal to our E1, which is right here. I don't want to write it out again. Times the alpha 1 minus 1 over alpha 1 squared, which is, in this case, our L over LU, which is equal to 3.55 over LU of cable 1 is 2.0 feet, 2.00. And then multiply that by the cross-sectional area of 1 plus E2 times alpha 2 minus 1 over alpha 2 squared. There's cross-sectional area of 2 plus E3 times alpha 3 minus 1 over alpha 3 squared. Times cross-sectional area of 3, alright? And then we use this same equation here for 485 newtons. And we'll copy that. Oh, that's not right. Delete. Copy that. And paste for 625. So those are a series of equations because we know E1, we know the alphas, and all of the cross-sectional areas. When you do this yourself, remember that these alphas will be different across the different forces because you'll be at different lengths. But again, we can use just our normal total length over the unstretched length is equal to alpha of the species. And when you solve these as a set of equations, I did these in Excel. You can do these however you like. You can even do them by hand. I don't recommend it though. When you set these series of equations and solve for E2 and E3, you come up with E2 equals 4.7438 times 10 to the 6th, and E3 is equal to 1.6728 times 10 to the 7th. Now, using these three E's, we can actually plug them back into our equation for force, because remember the original statement was to find the force required to separate blocks A and B to 5 feet when cable 3 is cut. So how we'll do that is now taking this whole equation, let me clean it up a little bit here. Copy. So now using this whole equation, we know that since we've cut cable 3, this section goes to 0, and we're left with this. And now that we've found E1 and E2, our new alphas are just equal to 5.00 feet times the unstretched length, which for 1 was 2.00 feet, and for 2 is 2.5 feet. So alpha 1 and alpha 2 equals 5.00 over 2.50. So we know our alphas. We know our cross-sectional areas because those never changed, and we can then solve for force. And solving for force gives us a final number, F equals, one second here, F equals 519.22 newtons. We should round this to 519 newtons. And that's our answer. Hopefully you found this useful. Thank you. Goodbye.